All right. Hello, everyone. Good morning or good afternoon, depending on your local time. I'm Fletcher Turner, and today we're going to be taking a look at Altair PSIM, presented by us here at True Insight. We're a channel partner of Altair, so we handle a lot of customers interested in the Altair suite of engineering software. Um, I have a colleague on the call with me, Tyler. It'll show up as Drew Buchanan. Um, he'll be available to answer some questions throughout the presentation. So if you have any questions, feel free to drop them in the Q&A or in the webinar chat. And the ones that Tyler can answer, he'll do so. Anything else that's left over, um, I'll save some time at the end of today's presentation to take a look at and hopefully get that answered for you. Before we get started, uh, Tyler has a poll, a little brief questionnaire just about your current work in power electronics. I believe he just launched that. Um, I will say it looks like I made a typo on the third question. That should be what area most closely aligns. So I apologize for that, everyone, but that's what that should say. So without any further ado, let's go ahead and get started. So our outline for today, I'll go over a brief explanation of what PSIM actually is, and then we'll just jump right into a demonstration. I'll show you an overview of the tool. We'll walk through a pretty simple, almost trivial example of a buck converter, but it'll still be nice. It shows the interface of the tool and how you can model things from something as simple as a buck converter all the way up to much more complex systems. SimView is the packaged results viewing software that comes with PSIM. So we'll take a little bit of time to look at that, some of the customization there, and then we'll take a look at implementing control within this power electronics software. And then lastly, I'll briefly touch on some of the design suites that come with PSIM, and I'll go more into what that means when we get there. So to start us off, what is PSIM? So it's a power electronics design and analysis software. So that means it can simulate just about anything in the world of power electronics, and it comes preloaded with a nice array of blocks and tools, starting with ideal components or more complex custom models. And there's also plenty of off-the-shelf ICs you can plug in. And I'll show you what that looks like as well. And in addition to being able to simulate this wide variety of different schematics, you can also implement control. You can design and analyze an extensive variety of control schemes, and that can be analog control or digital. There's plenty of tools within the software that can also handle that. Um, and also, I won't touch on this today, but if you have any questions, we can set up a time in the future to address this. PSIM integrates nicely with Flux and Flux Motor, which are also tools within the Altair suite of software. So you can make your models more customized if you're using a power converter attached to some form of motor. You could pull that in and model your system more accurately. So we'll go ahead, and I won't spend any time explaining what a buck converter is. I'll just say that we're going to walk through a very simple design of something you would see in the first chapter of your power electronics textbook back in college. So let me just pull that up right quick. Okay. So before we actually start designing that buck converter, this is kind of just the layout of the tool when you start a brand new project. So over here on the left, we have our library browser, which is where we can pull in all those different circuit elements that you're used to seeing in power electronics simulation softwares. And then the more common elements we've got down here at the bottom are normal passives, some switches, diodes, probes, and then some signal blocks as well. And I'll show you what that looks like as we go through the building of this right here. And like many softwares similar to this, we've have to set up our simulation control. Brought that up on a different window. So this is where we can set up the parameters of how we want it to actually run this simulation. So we can change our time step, our sample period, and then our total time. We have a couple other options here that have less to do with the accuracy of this simulation, more to do with just kind of how many resources you want to use in presenting or saving these results. So I'll just leave that as it is. And one other really nice thing that we can do is pull up a parameter file. So we have a couple of ways to access that. I'm just going to pull it from the library browser. We can just search and pull our parameter file over. So by default, this is just a blank sheet, but it accepts, it's very similar to OML. So if you're familiar with our other tool, Compose, or any other OMLs, such as Octave or MATLAB or FreeMat, it's a very similar language here. So you can declare variables, and you can also use some logic statements to define these variables. So I'll show you what that looks like. I won't make you watch me type the whole thing. I already have all this on another sheet. I'm just going to paste this right in. So what we're looking at are just some of our design parameters for the converter we're about to build. So we're going to say we want an input voltage of 24 volts and we want to get 12 volts out. So we can declare variables like that, or we can use some equations such as this duty cycle, V out over V in. There's some, I could have designed a better buck converter. It's pretty high switching frequency and a pretty wide tolerance on our voltage ripple, but that's okay just for the purpose of the example. So we can also do some math for the simple calculations for our inductor and our capacitor and load resistance. Now these values won't come out to anything that you could probably realistically get for an inductor or capacitor. So that's why you see I've got this L math and C math and then actual values that I'm using. So we can do this right here. We can show values. So we can see this L math and this C math are values that we get from our calculation, and then from there we can choose a more realistic component value. And I will say, you see here that I'm using the exponential notation right here, but this parameter file will also accept your standard metric prefixes, U for micro, M for milli, so on and so forth. But I'll just keep that as it is, and we'll keep this as it is. So I'll save this and close that. All right, so now I'll show you what it looks like as you actually start to pull some components in to build your buck converter. So we know we'll need our resistor. We can right click to rotate that and then just escape to get off the tool. We'll do the same for capacitor, right click, we'll place it. I'm actually going to leave some room, and I'll show you why later. We'll go ahead and grab a diode. I'll show you we can use a hotkey for that. So I just click the letter D on my keyboard, and then I can right click that as well and place that right there. Similarly, we can do I for inductor, place that, and then we'll need our voltage source. So I'll grab this guy right here. Again, I'm going to put it kind of further away from the middle of the converter, and I'll walk through why that is after we set up this initial design. So we also will need a switch. So we'll use the built-in MOSFET switch. Again, I could grab it down here from our quick access bar, or I can just hit M on my keyboard, rotate it to the orientation that I need, and I'll just pop it right there. So I'll just quickly connect these. Oops, if I could get it, I should probably zoom in a little. Let me do that. There we go. Probably a little bit easier to see now, and a little bit easier for me to see where my mouse is for making these connections. And we'll ignore that. That's just because I saved the parameter file a little too early. If it gives us a bug, that's okay. We'll sort that out. Let me also go ahead and throw just a ground on here. We don't have to draw these wires manually. We can just put them close enough together and it'll auto connect. A little black dot means that we've got the node connected there. And then so lastly, before I actually give this MOSFET a gate controlling signal, I just want to show off a little bit of how we can make these more complex. So right now, all these components are level 1 or ideal. So this is the inductor right here. I could change this to level 2, and you see I get a couple more parameters that I can plug in. And if the nomenclature is different or you're not quite sure what it's asking for, you can hit this little help button, and a window will pop up. And it shows for each level of the model, from ideal to the more complex one that it offers. It shows what each parameter is actually asking for, and in many cases there'll be a nice example to go with that. So I'm going to show it on something a little more interesting, this MOSFET right here. So same thing, if we double click on that, right now we're at the default ideal, but we can increase the complexity. We also have the option to start putting in real devices. So this device line right here, if I click this, you see we get a long list of manufacturers and part names. So I'll just click on a random one, and I can go to the device. And it'll take just a moment to load this. It has to search through all of the files for these devices. So depending on where you are alphabetically in the device you chose, it could take just a couple of seconds to pull up. And there we go. Now we have this specific device right here, and we've got a bunch of information that we can look at. We've got its electrical characteristics, we've got its VI curves down here for different temperatures. We could also, I won't show it today, but we could also extrapolate to other temperatures or interpolate depending on the values presented or the data you might have on hand. We can customize to make these devices as similar to the devices we're actually going to be using, as well as the operating conditions that they'll be subjected to. So this is a nice tool right here to get more details about your parts and make them as close to what you're actually planning on working with as possible. So I'll just close all this. For the purpose of this example, I am going to keep this ideal, and we'll move on. Oops, looks like I moved this out of place by accident. Just pop that back. There we go. Okay, so the last thing we'll need is actually our signal to control this right here. And you notice that there's not a whole lot of room right here to put any sort of switching subcircuit. So what I'm going to grab is just a quick label. I'll call it PWM. And then it's already rotated like I want, and I'll connect it. And so now I've got this block. And if I make this label anywhere else in our system, it's like a wireless connection. So we don't have to actually draw that wire. We could just cross over. But if you're anything like me, I don't like wires crossing over in a schematic, because if I don't realize there's not a black dot, or there is, I might think that they are connected when in fact they're just overlapped in the diagram. So I'm going to grab another label and I'll keep it PWM. So now we have our symbolic connection to our other PWM up here, and I'll place it right there. So now here is where we could build a simple comparator to make our PWM for this for the gate. I'm going to cheat just a little bit, and instead I'm just going to grab a square wave. I'll use my hotkey G for ground, and I'll grab this on-off switch controller, and I'll rotate it so it fits nicely, and I'll connect all this. So again, this I'm kind of skipping over some normal design customs, but it's okay because the logic will still hold just fine. So I'm going to go in here, and if you remember, I set the switching frequency in this parameter file as FSW, so I don't have to type a number in here. I can just type in FSW, and then for our duty cycle, same thing. We've already declared it in that parameter file, so I'll just make it D, and then everything else I'll just keep the same. So I'll close that, and now that's good to go. So the last thing I actually need to do is plug in the rest of those values that I set in the parameter file. So I'm just going to pull that up on a separate screen so I can make sure I'm using the exact same variable names that I used earlier. So for amplitude, we're going to plug in that VN that we defined. We can also give it a name. We can call that this V source, and we can display these over here. So there we go. We see that VN is its value, which is the 24 volts we declared in the parameter file, and name is V source. So same thing. I'll just go through and let me make that level 1. Our inductance is L. Our capacitance is C. And our load resistance is R. Okay. So now we've got everything defined within our circuit right here. The last thing we need to do, we could run this now, but we don't have any results yet because we're not telling it specifically what we're interested in. So we need to add a couple of probes to our system. So again, we can just hop down here and grab. We have a couple options. We have our series current probe. We have our voltage probe reference to ground, and then we can also look at the voltage probe between two nodes. So I'm going to look at V source, and then also our V load over here. And then let me rotate this, and we can also take a look at the PWM signal. Let me just make sure that's connected. There we go. So say we're also interested in our current. So I don't have to break this line right here. I can just hover. Let me make sure it's blue. Sorry, I'm not zoomed in far enough. There we go. So now it automatically will put that in series for us. And same thing on the output. So I'll go through and we'll call this VN. I'll actually display those. And then the same thing, IN. Over here, we'll say the out and I out. Oops. It's not really important to display them. It's more of a cosmetic preference. And then here we'll say VPWM. Okay, great. So now we have all of our probes in place. So we should be good to actually run the simulation. So we can hop up here and just run the simulation. We're getting that. There we go. And now that will automatically bring up our sim view, which is our results viewing software. So this is a pretty straightforward tool to use. We can add more plots. So I'll go ahead and, oops, it wants me to actually add a curve beforehand. So I'll just double click, and let's say we want to look at our VN and VOut on one plot. There we go. Let's go ahead and add another one, and let's say we want to look at our current in and out on this one. That's what we expect as that switch goes back and forth. And then let's add one more, and we'll pop this PWM right here. So you can see that our 10 millisecond runtime, we can't really see the finer details of what's going on. So let's change this x-axis so we can actually see a little bit more of the details. So I'm just going to drop that way down. There we go. So we can see our PWM, 50% duty cycle. We can see our currents and our voltages. So this isn't a super exciting case right here, but it's kind of a sanity check and a nice way to show what the tool is capable of. We can also put cursors on the line. So if we click this show values, we get this nice little box, and we get some cursors. So for example, we want to double check and make sure our output is really 12 volts at steady state. So we'll look at this cursor 1 on Vout, and we're at 11.97. So pretty close to our desired state right here. So that's nice to see. Now say we want to look at something a little bit more involved than just one of the direct probes that we're looking at in our system. So let me change this one. I'm going to remove the PWM because it's not super exciting to see that. We can also do some math to our signals right here to extract more information without having to export this data to another software. You don't have to dump it into an Excel file and then manipulate all the cells. You can do that directly in here with some simple functions. So we've got our basic operators and then just some standard math tools in here. So let's take a look at the integral of our Vout times, oops, I need to actually drop that down there, times Iout. And then we'll do the same thing. I can also manually type. I don't have to use the box that it gives us. Vn times In. And then I'll just add that over there and click OK, and it will calculate it. And so now what we've calculated here is the efficiency of our converter. So you can see if I pull up this table again, looks like I might have hidden it somewhere. There we go. So we can see that at steady state, we're looking at between 94 and 95% efficiency on this model. And again, that's probably higher than you'll see on any of your devices because we're pretty close to ideal here. But it's a nice demonstration of what the tool is capable of. Okay, so now what I'm going to do, so I'll move this back out of the way. And I'll get rid of that. So the reason I left such a wide gap here is to show off another pretty cool feature of this tool, and that's the fact that we can make basically anything into our own subcircuit, and we can use that subcircuit in other models. So say we're pretty pleased with this converter we've designed, I can highlight all of this. I guess I'll also probably need to grab this duty cycle as well. Oops, sorry, I need to zoom out just a little bit so I can grab all of that. I can right mouse click to drag everything around. Okay, there we go. So now I've grabbed all of the insides of this buck converter right here. Now, the only thing that we haven't highlighted is our input, our measurements, and our output measurements and our output. So I can right click on this right here and create a subcircuit. And then I'll just name this whatever makes sense. So in this case, I'll just name it demo subcircuit. And we get this device right here. So we can go in, and it takes some liberties automatically moving stuff around, but we can make this a little neater. And instead of actually doing that, I'm going to just pull up a model where I already have it pretty neat. So we've got this, this device now. Oops, enable. So we've converted it all into a subcircuit, and this is what it looks like on the inside. So we've got our VN plus and minus, and same for our V out. And then this one is also accepting a duty cycle from an external source. So again, I kind of cheated a little bit here. Instead of using a comparator, I just used the square wave block, which takes a duty cycle and delay and frequency. So you'll see that I just set the frequency to our switching frequency, delay to 0, and then we're just looking at this output Q, which plugs in as our PWM that now controls the gate. And you can also, what's really nice is, let's see, well, I think since I've already created it, it's not going to give me the option. You can change the location of these pins on the subcircuit itself to fit whatever layout makes most sense for what you're doing. So in this case, I put our VN plus and minus on the left and V out plus and minus on the right, and our duty cycle right here on the bottom. So with that all being said, we can start to look at this from more of a control perspective. So I'm going to keep going with the pre-built models that I have just for a couple of moments. So here, this is a very similar buck converter. The values are a little different, and here I actually use the comparator setup that we should. So before actually implementing a control, we need to know a little bit about our system. So again, for this simple buck converter, this is almost trivial, but again, the logic still holds. So we have all of the same information as before. These are slightly different values for this example, but now we've implemented an AC sweep. So the big three things we need to consider if we want to characterize the frequency response of our system. So once we've built our model, we need to have this AC sweep block. We need to have this AC probe, and we also need to actually add our AC perturbation to our switching circuit. So here we've got this frequency isn't super important in this block because we're going to name this V sweep. And you'll need to do a little bit of experimenting on your specific circuit to see what this peak amplitude should be to make sure you're still within the operating range of your device. And then over here, we're going to tell it the source name is V sweep. So now that this AC block will map to this AC voltage signal, and it will kind of ignore that 500 hertz frequency we established. And it will actually sweep through this 200 to 20 kilohertz. We can change this number of points. I'm going to lower this to 20. All that changes is the resolution of our model. And again, our start and end amplitude, this is a little bit what we have to play with just to make sure that our device still actually functions and we get measurable results. And what's nice is this last line, this frequency for extra points. So say you have a very complex model and you want to get results even quicker than PSIM already offers. We can lower this number of points, and then in areas of specific interest, we can add specific points that we're interested in. For example, on our Bode magnitude and phase response, we could actually get higher resolution at our knee or a crossover frequency or whatever you're interested in. So with all that being said and everything set up, we can run the simulation same as always. And we get, let me pull SimView back over into the frame. We still have our old results pulled up, but we can look at our Bode magnitude and phase response of our system. So again, pretty standard textbook example, but this logic applies to a wide variety of systems ranging from simple to complex. So let me pull this back over, get that out of the way. Okay, so after you characterized your system, one of the last big steps that many engineers are interested in is actually implementing a control scheme and measuring the effect with various noise or perturbations, something else being added to the system. So I'll jump over right here. So actually, let me move that over. I'm going to jump to, oh, sorry, no, that was the correct file. That was my mistake. So now what we have here is our same system with our buck converter in this subcircuit. We have our input and load on the outside. I'm going to actually move this away for a moment. And we have a PID controller. So again, you probably wouldn't manufacture a buck converter with such a simple PID controller in the real world. But for the sake of demonstration, we'll keep this as PID. Probably we only need the PI in this case, but just to show kind of the functionality, I'll keep it as is. So I've gone ahead and built out our basic structure where we've just pulled in our proportional block, and then we can also go into our library browser and find our integral block as well as our differentiator. So within these, we can set our gains and time constants, and specifically on this integrator, we can set an initial value as well as our limits to help with integral windup. So I'll just keep this as is. You can find these values analytically. You can use the frequency response we found in our previous stage, or you can do what I did in this specific example and just kind of play around with it. And I'll show you a more efficient way of doing that momentarily. So basically, we've got our output label right here connected to our difference block, and then our reference. So again, this will probably be more complex in your actual application, but we'll just assume that we're looking at a clean 12-volt reference compared to our actual output. So we can run this. And this isn't going to look too much different than what we've already seen, but you'll see that this plot, our green line, doesn't seem to fit. We can just redraw that. And now we see our response getting there quickly and maintaining steady state. And if we wanted to, we could actually zoom in on this. So let me just grab a zoom box. And we can actually see this ripple in our output. And if we wanted to measure that, we could add some grid lines. Not sure where there they are. So we can actually measure this difference between our peaks and valleys and see what our ripple turns out to be. So we're looking at 0.06 volts in this ideal setup. So you could measure this on a more realistic setup and see if it's within your specific tolerances. So I'll just turn all this off. Oops, wrong button. I'll move this back over here. Okay, so now what's a little bit more exciting is actually seeing how the control does with, some added interference. So I've prepared a couple of options here. This one is just a delayed step. So we'll increase our voltage by 1 at 5 milliseconds. So, I don't know what potentially would cause that in your specific setup, but if we have a change in input voltage, we want to make sure that our output stays the same. And we can verify that using PSIM. So I'll pull this back over. We're still zoomed in, so I'm going to return to, well, let me do this. Sorry about that. There we go. And I will redraw. So we can see our control isn't super robust because we can see that for the conditions it was designed for, it does pretty well. And then when we add that 1 volt on the input, we still stay close to 12 volts. We have a lot more ripple than we originally had. And that happens right there at that 5 milliseconds. We can also swap this out and see if we don't have the cleanest power bus. We can plug that in right there. And this is just a small sinusoid at 1,000 hertz of just consistent noise in the supply voltage. So we can run this again, and we can see now again our control. It has a larger ripple, but it still keeps it relatively close to 12. So this is where we could start kind of fine tuning it for these situations. This is where we can modify the simulation just a little bit to, instead of having to change one value, from 7.5, change it a little bit, run the whole simulation again, we can run the whole thing in real time. So that's exactly what I'm going to do. I'm going to set up a scope first. Let me find just our single channel scope. And let's say I want to measure the voltage right there. And now we need to make a couple more changes to tell this to run consistently. So I'm now going to change this to free run, and our total time is grayed out because it's going to start the simulation and it's not going to stop it. So it'll be like we actually built this and we hooked up an oscilloscope directly to it. So that's what our interface will look like. And then whatever values we're interested in actively changing while the simulation is running, say we had a magic knob that could change this proportional gain, we can actually go to runtime variables and turn gain on. So now what this means is as it's running, we can change this value right here. And let's say we want to do it for our integral term as well. So let me, oops. Sorry, it's a pretty tiny box that I'm aiming for. There we go. I'll keep up this one right here. Okay, so now I'm just going to run the simulation and look at our output. So it might be hard to see over video call, but this signal is actively moving right here. And we could say we want to see what increasing our proportional term does. So we want to blow it up way bigger than it was. So now I can see we've got a bigger ripple than before. So we can drop that back down. And then we can see that ripple gets smaller. And we can play with that. We can also play with our integral term. Say we want to make this 0. Why not? And then we can see again, we get some more steady state error. It doesn't really settle out. And we can just kind of go and fine tune this as we see fit for the specific model we're working on. So that's kind of the process of, let me stop the simulation. That's kind of the process from beginning to end of starting with scratch, setting up your system with your different components, whether you want to keep them ideal or turn them more complex. We can start measuring all sorts of values from that system, whether that's individual signals or the actual performance or efficiency. We can analyze the frequency response. We can characterize our system, and then from there we can actually implement some control. And so again, this is a pretty simple control, but we could get a lot fancier with it and start measuring what the inside of these control signals are doing, as well as the effect that has on our system. And we can even look at it as if we've really built the system on our lab bench, and we're measuring those results live. So before I open up the floor for questions, I do want to just briefly point out, close that, some of the extra features within PSIM. So that's the design suites that are part of PSIM. It comes with many great starting points for a lot of different kinds of common circuits. And they're also just great examples of how to use some of the functionality within the tool. If the help block if the help window isn't enough, these range from simple to complex systems that show you how everything can piece together. And they're really nice, actually, because if you are using it to learn the tool or as a jumping off point for whatever you're building, there's a nice parameter input panel for a little bit easier interactivity. And I'll show you what that looks like in just a moment. And they cover a wide variety of applications, from obviously power to motors. That kind of ties back into what I mentioned at the beginning of this, being able to use custom motors, motor drives. We can use that in electric vehicles, hybrid electric vehicle applications, as well as electromagnetic interference. So I'll just pull this right back up for a moment. So the way we access those are our design suites up here at the top. So we can pick whichever we're most interested in the moment. So I'll just stick with buck converter and unpack this. And so now you see we've got this pretty nice fleshed out buck converter that uses peak current control. So it kind of showcases a lot of the different functionalities that I just walked through, but also in a more real world setting, closer to real world anyway. And so this is what I was saying, this parameter input panel. So this is found on most, if not all of those, these design suite circuit models that come preloaded. So this is nothing but a nice clean way to go in and edit this parameter file without having to scroll through, especially if you have complex parameter file with a lot of logic going on and whatnot. So this would allow you to manually change, say our input changed from 24 volts to 30, then we could just update this parameter file and rerun the simulation. And we can combine that with looking at some results in real time, or just comparing the results in SimView based on these changes. This right here isn't a direct feature within all the other custom schematics you might build, but you could achieve something similar with another tool that I've mentioned, Altair Compose. And so again, if you're interested in that, we've got plenty of resources to help you get going on that. So with all that being said, looks like we have about 15 minutes left. So I'll now cut over to some of the questions that have popped up. And also feel free to ask any more questions. So is it possible to verify the total harmonic distortion directly in the plot, or we need to add that block in our schematic? So that's a good question. I didn't prepare an example with that, but you can measure the THD directly in SimView, as well as a couple other things, power factor and whatnot. So yes, the short answer to that question is yes, it is possible to verify that directly in the plot. And also we have a question, can we add SPICE models to make more realistic models? So there is a SPICE link within PSIM. I will be honest, I'm not very familiar with that link right off the top of my head. But long story short, yes, PSIM can be used with SPICE models, but from what I know, it can be a little difficult to use, and typically engineers will build what they need directly within PSIM. So hopefully that answered your question regarding SPICE. So yeah, I'll stay open for questions now in the Q&A or within the webinar chat. And while I wait on anyone to pose any specific questions, I'll go ahead and bring up that we're True Insight. If you are interested in learning anything else about any of the Altair electrical tools or the mechanical tools, or any of them, you can visit us at trueinsight.io. We've got plenty of blog posts there that walk through some examples of how to use the softwares, and that ranges from just some simple how-tos, some basic intro stuff, up to some more fun applications. I know one of my colleagues actually simulated the heating of the doorknob, like in the movie Home Alone, to see if it was realistic. So you know, there's just some fun applications. Oh, I have a question. Can you clarify or summarize what this can do that LT Spice can't do? So yeah, there's at the surface level, they're pretty similar looking tools, PSIM and LT Spice. What I'll say, actually, I'm going to write down your name, Mike Miles, and I'll grab your email so I can send some more information your way after this. But briefly, PSIM has a wider range of complexity available, as well as from my use of Spice, it's a little easier to use, especially easier than LT Spice. And you can customize how you want to retrieve and examine the results a little bit better. They are similar tools for similar applications, but overall, I think the user experience is more streamlined, more customizable within PSIM. But I can definitely get you some more direct comparisons. We might, I won't make any promises, we might have a benchmark comparison between the two. I'll have to double check and see. And if we do, I'll gladly send that over to you. Okay, we have a couple minutes. Oh, here we go. When we perform the fast Fourier transform for a signal in SimView, the magnitude of the signal corresponds to the RMS or peak value. I believe it would be the peak value, not the root mean squared, but I will double check that, and I can, let me also write down your name. But yeah, I can send over some documentation regarding that. That is one thing I didn't show, but it is relatively easy to do the FFT within SimView. It's as easy as a right click and one or two buttons to get there. Okay. Keep it open for questions for another couple of minutes in case any of you are typing anything up. If you don't have any other questions, I appreciate everyone joining in today. I hope this was a valuable experience and you learned a little bit more about PSIM. And if you're interested, like I mentioned, you can reach out to us you can find us on our website, www.trueinsight.io. There's plenty of ways to contact us directly with any questions you might have, or if you're interested in learning more about a software or actually acquiring any of these softwares, you can do all that from our website. We also have a lot of helpful videos on YouTube, on our True Insight channel. You can also find links to those videos on our website. So it's really the one-stop shop for all your Altair questions. You can reach out to us directly there, and we'll get the answers back to you.